Hello everyone, welcome back to Diligent Automation. Today, I'll be designing the complete system architecture and bill of materials (BOM) for a sugar refinery automation project. Before we begin, I'd like to clarify that this is not a greenfield project. The refinery is already in operation using legacy PLC hardware, with most of the process currently running in manual or semi-automatic mode. The client's objective is to modernize the entire automation system by replacing the legacy control hardware, redesigning the complete control architecture, and developing new PLC and SCADA software to achieve fully automatic plant operation. The purpose of this video is not just to show the final design. I want to walk you through the engineering thought process involved in designing a large-scale industrial automation system. My goal is to help engineers, system integrators, and automation professionals understand how real industrial automation projects are engineered, from system architecture and hardware selection to software development and implementation. This type of project is not new to us. Around 6 years ago, our team successfully delivered the complete PLC and SCADA software for another sugar refinery belonging to the same group in a different state of Nigeria. Before we begin designing this new control system, I'd like to give you a brief overview of that previous project. This will help you understand the refinery process, the major process areas, and the automation philosophy, providing the necessary background to follow the system architecture we'll be developing throughout this series. Whether you're an automation engineer, a system integrator, or someone looking to learn how large industrial automation projects are designed, I believe you'll find this series both practical and valuable. So let's get started. For this project, we have selected a redundant FactoryTalk View SE distributed architecture to ensure high availability and reliable plant operation. The SCADA system consists of two physical server machines, each hosting multiple VM. These VM are configured to host the following FactoryTalk components: HMI servers, FactoryTalk View, SE clients, OPC server, FactoryTalk directory, Microsoft SQL server for historical data storage, alarm and event server. This redundant architecture provides seamless failover, minimizes downtime, and ensures continuous plant monitoring and control. The PLC is Allen Bradley ControlLogix L73 controller with all remote I/O in 1734.io platform. The project includes approximately 2,500 digital and analog I/O points, making it a large-scale industrial automation system. In addition to the remote EOs, the plant contains 8 intelligent MCC panels, comprising approximately 400 intelligent motor starter devices, including direct online starters, soft starters, variable frequency, drives. The 1734.io racks communicate with the ControlLogix controller over Ethernet IP with DLR network. This redundant ring network provides high availability and maintains communication even if a network cable or switch path fails. The intelligent MCC panels communicate with the ControlLogix controller over PROFIBUS network. The ControlLogix chassis is equipped with both an Ethernet IP scanner module and a PROFIBUS master module, enabling seamless integration of Ethernet IP-based remote I/O with PROFIBUS-based intelligent motor control devices. This architecture combines high-performance PLC control, redundant industrial networking, distributed remote I/O, and intelligent motor control to deliver a robust, scalable, and reliable automation system capable of supporting the operational demands of a modern sugar refinery. Before we dive into the system architecture, let's take a quick look at the overall refinery process. I won't be explaining the complete sugar refining process in detail because the primary focus of this channel is industrial automation engineering, not process technology. Also, discussing the complete manufacturing process is beyond the scope of this series and respects the confidentiality of the project. One important point to note is that this refinery does not have a sugar mill. Instead of processing sugarcane, the refinery imports raw sugar from other countries. Since the plant is located close to a seaport, the raw sugar is unloaded directly from ships and transported via a dedicated conveyor system to the DOM silo where it is stored. From the DOM silo, the raw sugar is conveyed to the mingler and melter section, where the refining process begins. Here, the raw sugar is mixed with syrup and heated to produce a sugar liquor, which is then transferred to the next stages of the refining process. The pre-clarification section prepares the sugar liquor for further purification by heating it and removing impurities through chemical treatment before the main clarification stage. The clarification section removes the remaining impurities from the sugar liquor by adding clarifying chemicals and separating the resulting mud, producing a clear liquor for further processing. The pan section concentrates the clarified sugar syrup through evaporation and crystallizes the sugar under controlled vacuum conditions to produce sugar crystals. The centrifugal section separates sugar crystals from the mother liquor using high-speed centrifugal force, producing clean sugar crystals for the drying process. The sugar dryer removes the remaining moisture from the sugar crystals using hot air, ensuring the required quality for storage and packaging. The molasses tanks store the final molasses, while the recovery melter section reprocesses off-spec sugar and recovered crystals, maximizing sugar recovery and minimizing product loss. The refined sugar silo stores the finished sugar before it is conveyed to the packaging section, ensuring a continuous and efficient production process. Other utility sections. So far, we've discussed the refinery process, the SCADA architecture, and the PLC hardware used in this project. Now let's move to the PLC software. A large industrial automation project is not just about selecting the right PLC hardware. The software architecture is equally important. Well-structured PLC application makes commissioning easier, simplifies troubleshooting, and allows future modifications without affecting the entire system. Let's open the Studio 5000 project and take a look at how this application has been organized. Let's begin by looking at the controller and I/O configuration of this project. At the top, we have the Allen Bradley ControlLogix L73 controller, which serves as the PLC of the entire refinery automation system. Some of you might be wondering why this project uses the L73 controller instead of the newer L83 processor. That's a very good question. The reason is that the complete PLC panels, including the controller hardware, were already designed and supplied by an OEM from Brazil. Our scope of work began later when we were entrusted with developing the complete PLC and SCADA software for the refinery. Since the hardware platform had already been finalized, we developed the entire automation application using the existing ControlLogix L73 controller. This is quite common in large industrial automation projects where one organization supplies the hardware while another specializes in software engineering, commissioning, and system integration. Now, let's look at the communication modules installed in the ControlLogix chassis. You'll notice that the controller uses two Ethernet communication modules, each serving a dedicated purpose. The first module is the 1756-EN2T. This module is dedicated to upstream communication, allowing the PLC to exchange data with the SCADA system and other higher-level industrial networks. The second module is the 1756-EN2TR, which is dedicated to communication with the distributed remote I/O system. The remote I/O stations are connected using the device level ring or DLR protocol. One of the major advantages of DLR is media redundancy. If a network cable is accidentally damaged or disconnected, communication is automatically maintained through the alternate path in the ring. This significantly improves system availability and helps prevent costly production downtime caused by a single cable failure. Moving further down the I/O tree, you can see that the field I/O is distributed across multiple 1794 Flex I/O racks connected over the Ethernet/IP network. This distributed architecture reduces wiring, simplifies installation, and makes future system expansion much easier. The controller also uses PROFIBUS DP scanner modules to communicate with the intelligent MCC panels. Through this communication network, the PLC exchanges motor start and stop commands, operating status, protection information, alarms, and diagnostic data with the MCC. Overall, this hardware architecture provides a reliable, scalable, and highly maintainable control system, ensuring high availability while simplifying commissioning, troubleshooting, and future plant expansion. Now let's take a look at how the PLC software has been organized. One of the most important aspects of any large industrial automation project is having a well-structured and modular software architecture. Instead of writing the entire application in one large program, the software is divided into multiple programs and routines, with each one performing a specific function. The software architecture in this project is developed based on the ISA 88 modular programming philosophy. Although ISA 88 was originally developed for batch processes, its concepts of modular equipment design and reusable software are equally valuable in large continuous and process industries such as sugar refining. Following this methodology, the complete plant operation is divided into control modules and equipment phases. A control module represents an individual field device or a small group of related devices such as motors, valves, transmitters, or other field instruments. Each control module contains all the logic required for that device, including command processing, status monitoring, interlocks, permissives, alarms, fault handling, and diagnostics. Because every similar device follows the same software template, the code becomes highly standardized and reusable throughout the project. Above the control modules are the equipment phases. An equipment phase coordinates multiple control modules to perform a complete process operation. Instead of directly operating individual outputs, it supervises the sequence by issuing commands to the required control modules and monitoring their responses. This creates a clear separation between device control and process sequencing, resulting in software that is easier to understand, maintain, and expand. Within each program, the logic is further organized into routines. The main routine simply coordinates execution by calling individual routines. Each routine is dedicated to a specific process area or engineering function, making the software highly modular and easy to navigate. This architecture provides several engineering advantages. Multiple engineers can develop different sections of the software simultaneously without interfering with each other's work. Testing and commissioning become much faster because every control module and equipment phase can be verified independently before integrating the complete process. During maintenance, engineers can quickly identify the relevant module instead of searching through thousands of ladder logic rungs. This standardized approach was one of the key reasons we were able to complete the software development for this entire sugar refinery in just 62 days. For a project of this scale, involving thousands of I/O points, multiple process sections, distributed flex I/O, and intelligent MCC panels connected over PROFIBUS, achieving this timeline required not only engineering expertise but also a disciplined and modular software architecture. We are proud of this achievement because it demonstrates how applying proven engineering principles, such as the ISA 88 modular design philosophy, can significantly improve development speed while delivering a reliable, scalable, and maintainable automation system. This brings us to the end of today's session. In the next episode, we'll explore how to prepare a complete BOM using Rockwell Automation's integrated architecture builder. Starting from the customer's functional requirements, we'll walk through the complete hardware selection process, including PLC controllers, I/O modules, communication interfaces, network components, and accessories. You'll learn the same systematic engineering approach used to develop accurate and professional BOMs for real industrial automation projects. Before we conclude, I'd like to share an exciting announcement. In addition to this Real Industrial Project series, we're also launching the Diligent Automation Programming Excellence series, starting with the Rockwell Automation platform. This series is designed for both beginners and experienced automation engineers, focusing on industry-standard PLC programming and real-world engineering practices. Topics will include PLC programming standards and best practices, UDT and AOI development, modular equipment programming, sequential programming, servo motion programming with Rockwell Kinetics, advanced motion control, advanced PLC programming, process control, FactoryTalk View SE development, commissioning, real industrial project programming reviews. Our goal is to share practical engineering knowledge that helps you build reliable, scalable, and maintainable automation systems using proven industrial methodologies. I also consider creating and sharing these videos as an opportunity to continuously improve my own engineering and presentation skills. Your feedback is extremely valuable to me, so if you have any suggestions or ideas for improvement, please share them in the comments. Your constructive feedback will help me create even better technical content for the automation engineering community. If you enjoy this content, please subscribe to Diligent Automation and enable notifications so you don't miss any upcoming videos. Thank you for watching, and I look forward to seeing you in the next episode.